Okay, good morning everybody. Welcome to the next session on basics of video technology. So this is where we stopped last time. Basically we looked at the spectrum, the FFT spectrum of an amplitude modulated signal. And you can see in the middle we have the carrier, which is the strong peak, and then to the sides off from the carrier frequency and the upper sideband here and the lower sideband, we have this, the actual information that is transmitted. So the sidebands carry the information twice, once on the upper sideband and once on the lower sideband. And then we have the carrier, and the carrier is just good for a simple demodulation in the receiver. So we saw basically demodulation in the receiver is basically a mixing of this AM signal with its own carrier. And mixing with its own carrier means we also have a component which is back at the baseband, and then we just need to apply low-pass filtering to keep this part at the baseband to have the demodulated signal. So this demodulation can also be done in software, which you can see here in this Python example. And as seen last time, we have for the demodulation in software two carriers, one sine and one cosine carrier, which we then use for simple demodulation. So here we can see the modulation, right? So this is what we did last time. We have our Sine Modulation carrier here, called Träger in German. And then we have our information that we want to carry, called Ton in German, is sound. Another sine function but at a much lower frequency, and then we just do the modulation by getting a DC offset to a tone, which you can see in the beginning, and then we multiply it with a carrier. And in this way we have the amplitude modulation. So I can simply do it here in my terminal window. So when I open the terminal window here, open the terminal, I can just make this a little bit bigger. And open IPython minus Pylab. Then I have the interactive mode of Pylab, and I just can copy and paste these three lines to have my amplitude modulation. So here you go. So now we have the amplitude modulation, and we can just check it by plotting the AM. Right, and here you can see, like last time, the amplitude modulated signal. So we see the blue color, which is the very dense waves of the carrier wave, and then we see this amplitude fluctuation, which is the amplitude modulation. Right? So here in the envelope, we have the actual information that we want to transmit. And the carrier wave doesn't carry information for the decoder. So now we want to decode it, and for the decoder we now make two carriers, one sine carrier and one cosine carrier that you can see here. And we just mix the AM part that we just saw, the AM, we mix it with this local carrier. Right? Mixing means multiplication, as we see here. So we just take those two carriers, and each time we multiply it with the AM carrier. So I can also do that here, copy and paste. So now we have two down mixes, one for the sine and one for the cosine. And now we can plot it to see what we have. So first is the sine part, which we can see here. So again, copy and paste. can see the demodulated version for the sine carrier. So this looks now different, right? So now we have this fluctuation only on top, and below there is no fluctuation anymore. And then you can also see that it's all positive. Right? So this comes out of the sine carrier being the right phase. So the sine now has exactly the same phase as the carrier from the transmitter side. So basically we downmixed it now to frequency 0, and this is basically the DC offset that we use for modulation. Right? Remember, we have this 1 plus 0.5 times tone, and this is exactly what we now see here. But also we have still the carrier, and the carrier needs to be removed using our low-pass filter. So after low-pass filtering, basically we smooth this curve, and then all what's left is this 1 plus 0.5 times tone. So it means we're on the right way. So this looks good already. So we are halfway there. So this is this downmix. So now we need to basically get rid of the high frequency content, the dense oscillations which caused this blue color in this plot. Right, and we do that with our low pass filter. Maybe I should also show you the downmix cosine. In this case, the cosine downmix is actually not so interesting. So here we have cosine, cosine. So, what's the difference now between the sine and the cosine version?
It has a negative.
Yeah, exactly. It actually looks almost like the original amplitude modulation, right? So, what happens if we now apply a low-pass filter to this signal? What do you think? So observe that we have the symmetry between positive and negative values. Right? It goes up and goes down. And now imagine we apply a low-pass filter. Remember, low-pass filter is basically smoothing over time. So what happens if we apply smoothing to the signal over time? You know?
It's going to become just a line horizontally.
Yeah.
That's 0.
Right, exactly. So if you have values like +1, +1, -1, +1, -1, and you take the average, then the average is 0, right? Because the average between +1 and -1 is always 0. And this is what will happen here too. So if you apply a low-pass filter to this part, it will become 0. So in this case, actually, we don't even need this cosine part. But imagine we have a phase shift on the transition between the transmitter and the receiver. Then we don't know if it's a sine or cosine or in between. Right? And that's why we need to have these two carriers. Basically, both together give us a robust decoding or demodulation. Yeah, so how do we get a low-pass filter? Basically, we already saw a low-pass filter in the context of an FFT or a DCT. Basically, we keep the low-frequency components and attenuate the high-frequency components. So when we have the FFT domain or the DCT domain, we can just apply our mask and multiply the high-frequency components with 0, and multiply the low frequency components with 1 and then do the inverse transform. Remember? So in this way we did, for instance, the downsampling of the color components in the spatial image domain. So here basically we can take the high frequencies in the frequency domain and set them to 0 with a mask. And we already saw that we got the same result or a similar result when we transform the mask back to the original time domain or space domain and convolve the result, the filter, with the image. And Python has a very practical library that can design a digital low-pass filter for use in the time or space domain. So if we don't want to do it with our frequency domain mask, we can just use Python functions. So for that we should know the low-pass cutoff frequency. So we should know at which frequency we want to go from passing to stopping. Right. And it should have a cutoff frequency larger than the highest expected signal frequency. Right. We don't want to attenuate our signal frequency, so that's why it has to be higher than the largest expected signal frequency and lower than the carrier frequency. Right. Because we want to attenuate the carrier frequency, or rather the doubled carrier frequency, because that's coming from the sum in the mixing process. And that is usually a wide range. Usually the modulated frequencies are much lower than the carrier frequencies. For instance, if you think about medium wave radio, you have a carrier frequency of 1 megahertz, and you have signal frequencies going up to maybe 4 kilohertz. Right? So it's an order of magnitude in between them. So in our case, the signal frequency is 2 hertz. Here, this 2 hertz which you just saw, and the carrier frequency is 1 kilohertz. Again, almost an order of magnitude. So we can just choose the cutoff frequency in a wide range, and here I used 500 hertz. Right? So it's actually half the carrier frequency. Our sampling rate is 32 kilohertz, and so the Nyquist frequency is 16 kilohertz. Nyquist frequency is 16 kilohertz. It sounds better. Yeah, so the cutoff frequency normalized to the Nyquist frequency is 500 divided by 16,000. And this normalization is used by our filter design function. So that's kind of an unusual normalization. Usually what you see, if you have frequency plots, then 2 pi is the sampling frequency. Right? But here in this case, 1 is the Nyquist frequency. So that's kind of unusual, so you have to keep it in mind. So I use this function called IIR filter, which designs infinite impulse response filters, simply because it's easy to design and implement. So basically it has an infinitely long impulse response, which is similar to analog filters like RC elements in the diode demodulation. So RC stands for resistor and capacitor. Right? So remember, this is what we had in the diode. We had a capacitor, and then we had a resistor coming after it as a low pass. So this capacitor is often left out, but it's implicitly meant to be at the next entry of the next stage. Yeah, so this function from Python, this IIR filter, expects as one of its arguments the cutoff frequency normalized to this Nyquist frequency. So here's the example. This IIR filter function is part of the library SciPy signal. So first I import it here, and then I call this filter function, The first entry, the first argument is the order, which means the number of coefficients in B and A. B and A are the coefficients for the feed-forward and feedback part of this filter. So this is the feed-forward part going from the input to the output. And A is the feedback part going from the output back to the input. So altogether we will have 4 coefficients. Then this is our cutoff frequency, normalized to our Nyquist frequency of 60,000 Hertz. This RS is the stop-band attenuation that we would like to have, 60 dB. 60 dB is always a good number for filters. Then B-type, the filter type is low pass. Yeah, and that's basically already it. So then B and A contain our filter coefficients. And we can actually also do that in our terminal window. Copy, paste. So now we're already done. So you can see our filter was able to compute B and A almost instantaneously. And when we look what's inside, B now has indeed 3 coefficients. Interesting. And A has 2 coefficients plus the first entry, which is always a 1. So actually it uses as the highest coefficient, so 0, 1, 2. So it has 3 coefficients in B. So that means the first coefficient is the coefficient for the undelayed input, the second for delayed by 1 sample, and the third for delayed by 2 samples. Similar for A, but now this refers to the output. So the factor 1 is applying to the output. Basically, this one just comes from being a feedback system. And this is then, the next one is the delayed output by 1 sample, and the last one is delayed by 2 samples. Yeah, so now we need to,
So I want to ask the argument there, B-type, can it be any string variable?
No, it needs to be an array, it needs to be numbers.
We will always use the low pass as a B-type.
Oh, you mean this one here?
Yeah.
No, you can also use high pass, that's another option, or bandpass. Right, and maybe there are more options, but I don't quite remember. Actually, we can see it when we look at the help function. You can type help IIR filter. Do you know this help function?
Yes.
I find this very practical actually. So then you actually get the different possibilities. So here you can see F-type, B-type. Here's the B-type. So this is what we're using here. And B-type. Here we have the choice bandpass, low pass, high pass, band stop. And default is bandpass. So that's why we need to set it, because we don't want a default. We don't want the bandpass, we want a low pass. Yeah, so this is actually quite useful to see the choices that you have for an argument. Yeah, good question. So now we have coefficients for a filter, but they don't say much to us, right? It's just numbers. But we would like to know if this filter is really good, right? And for that we need to plot the frequency response to see how wide the passband is, and also to see how much attenuation we get in the stop band, and how wide the transition band is from the passband to the stop band. Right? We need to check the quality of the filter that we obtained, because there's no guarantee. We specified this 60 dB in the stop band, but who knows? There's no guarantee that we get those 60 dB. depends also a lot on the order that we choose. So here we actually chose quite a low order. 2 is quite low. So maybe it doesn't work. Right? So that's why we have to check it. And we do that with our function frexy. Frexy takes the coefficients, the b and the a, as argument, and then computes the frequency response at finely spaced frequency intervals. Right? And these frequency points are returned in the array W. So W contains the frequency points at which frexy evaluated the frequency response of our filter. Right? And then H contains the complex valued frequency response, so in magnitude and phase, or real and imaginary part. In our case, we are just interested in the magnitude because we want to see how much attenuation we get. So that's why we plot the magnitude as the function abs. So abs for absolute computes the magnitude. Remember how we compute the magnitude from a complex number? Again?
The absolute, we use the absolute function to get the real.
Yeah, so what does this absolute function do?
It gives the real values, the absolute.
No. The real value is obtained by the function real. Right? There's the function real, and then there's the function, I think, imag, which gives the imaginary part. So what does abs do?
Remove the floating values.
Imagine you have to compute the abs function. How would you do it? Yeah.
For a complex number, it's the length of, if you think of it like a vector, it's the length of the vector
Yeah, right.
towards the point in the complex surface.
Right. So how do you compute the length of the vector?
Square root of the sum of the squares of its components.
Yeah, exactly. So in this case, it's real part squared plus imaginary part squared, and sum them and take the square root. So it's square root of imaginary part squared plus real part squared. And that's it. Remember? Complex number calculations. So this is basically what abs is doing. Right? So it's basically just one line of code. It's really simple. So in that sense, we don't really need it because it's so simple. We could just write real squared plus imaginary squared and square root of it. But this is even shorter. Right. So and then we can plot it. So x-axis is frequency, y-axis is the magnitude. Yeah, so if you're not so familiar, memorize it, right? Abs is the sum of squares and square root of it, because it's important. So this is now the result. Right? So what do you think? Does it look reasonable? Is this what we would expect? Well, first, where is our cutoff frequency here? Where should it be? It's kind of hard to say because we specified it in a different normalization. And you can see here, we have the normalized frequency where pi is the Nyquist frequency. Right? So in frexy, always pi is the Nyquist frequency. But in our filter specification, we have 1 as the Nyquist frequency. So basically we need to renormalize our values. So instead of having 500 divided by 16,000, right, this is what we got from the normalization to IRR filter. We now need to multiply with pi, right? because then pi will be Nyquist. Make sense? So that means, so that means roughly 0.1 in this normalization will be our cutoff frequency. So then we can check it. What do you think? So 0.1 should be somewhere here, right? Actually, it doesn't look too bad, but it's kind of hard to say because it's very narrow, and also it quickly decays to very small values. And those small values are also hard to say here in this plot. Yeah, so this is what I just did here. Renormalizing to pi as Nyquist, so we get 0.09 or approximately 0.1. So it's very close to the observed plot of the magnitude frequency response. Yeah, and maybe I can actually try the same here with, instead of apps, I can do SQRT of real of h plus Imag of h squared. Let's see if that works. Is this correct? Did I miss a bracket? Yes, it might work. Yeah. Can you see that this is the same? So abs is really just this formula. Right, and here I could, for instance, zoom into the passband region here to more closely check it. So here we have 0.1, and here we have 0.6. So that actually looks reasonable for a passband, right? So usually at the edge of the passband you have something like square root of 2 of attenuation. So close to 0.7, which is roughly what you observe here. So the passband actually looks okay, but then it's kind of hard to say how much attenuation we have in the stopband. Oops. So what we do here is we apply the logarithmic dB scale. Right? So instead of directly plotting the abs, the magnitude, we now plot 20 times log 10 of abs. Right? And we use the factor of 20 because here we assume that we have voltages or currents and not power. Right? Because what we get out of the filter is usually voltages or currents. So that's why we now apply this 20 times log base 10. Does it make sense here? 20 times log base 10. So this is how we convert factors to dB. Yeah, this one. Do you all remember? Did you all have it before? If not, memorize it. That needs to be in your brain. Right. Yeah, so basically here you can see we do the plot, again with W for the x-axis, but now instead of just abs h, we use 20 times log 10 of abs h. And then we scale the axis, because we don't need more than, say, minus 80 dB attenuation to get more fine resolution. Yeah, then let's see what happens. Copy. So this is what we got. So now the y-axis is the dB scale, and remember we wanted to have something like 60 dB attenuation. So here you can see the 60 dB, And we get the 60 dB about normalized frequency 2. So let's see, you can actually see it more precisely when we use the mouse. You see here on the lower right hand corner, you can actually see the precise mouse coordinates for x and y. So now I try to be at 60, y should be minus 60. So roughly here. Yeah, and that means x is roughly 2. So we reach the 60 dB, but only at relatively high frequencies. That means we have a quite wide transition band from 0.1 to about 2. Right? So the filter is actually not that great. It looked nice on our absolute scale, but it doesn't look so nice anymore in the log dB scale. Okay, so this basically reveals the shortcomings of this filter. But since it's simple and cheap, we take it anyway. Right. So we have to be aware that this is not a good filter, but it's doing somewhat of a job. Right, so this is the picture that we got. Yeah, so we see that on the dB scale we have only relatively slow increase of the attenuation towards high frequencies. But it should be sufficient for our purposes because we do not have to suppress any neighboring carriers. Right? So our receiver doesn't have to be so sophisticated because we are the only one transmitting basically. Yeah, and now we can apply this filter to our two mixed signals, the downmix AM and the downmix AM sine and downmix AM cosine, and then calculate the magnitude again. So this is now getting rid of the carrier, right? The blue color that we saw in the previous plots. Now we have our filter. Here you can see I apply the filter using the function L-filter. L-filter is also part of SciPy signal, and this is the function that applies the filter that we just computed with IIR filter. Right, here you can see B and A as the argument for L-filter, and then you can see here the signal to be filtered. So now L-filter filters the signal using the coefficients. Yeah.
Does Python support 1 asterisk as multiplication? We're having 2. What if I use 1?
You mean what?
Sine double asterisk.
This one here?
Yes.
And
What if I use 1?
Yeah, what is the double asterisk?
Do we use it for multiplication only?
What do you think? What does double asterisk mean in Python?
And I'm asking if it is for multiplication.
No. Actually, I just applied it. When you look at my code. Here. Do you see it? So what does it mean? What do you think?
It's for power.
Yeah. Right. The power of 2. So here I want to square it, right? And instead of writing real part times real part, I write real part star 2, which means square. Yeah. So in MATLAB or the C programming language, we have this this little head or this kind of triangle symbol. In Python, you have this double star, right? So that's kind of unique for the Python programming language, and it has the advantage that this triangle thing is at different international keyboards at different places, right? Where star is more easily to reach. Star is also at different places, but usually more easily to reach than this up thing. Yeah, and for this triangle, usually you need to type this triangle, and then space to actually get it to see, because it's often used to for, say, this key followed by 2 makes this raised 2. Okay, so you only see this triangle when you type this key followed by space. So that's probably why they decided to use this double star here instead. Yeah, like this, right? So I needed to get 2 keystrokes to get it. Actually, this also needs 2 keystrokes. Yeah, makes sense? So here now we have 2 filtered versions. One low-pass filtered version for the cosine and one for the sine part. So what will the output of low-pass downmix AM cosine be? What do you think? What will be the output? We just talked about it 10 minutes ago. Yeah, exactly. It will be 0, right? So in our case, this second part will disappear, but in general it will not. This first part will contain our, what will it contain? Remember, this part had our sine wave, the slow sine wave, and below it, it had this dense carrier wave. So after low-pass filtering, what will we get? No?
We're going to receive the original signal that we've transmitted.
Yeah, basically we clean up the blue color below the line. Right? All we will left with is this smoothed envelope. And we will get 1 plus 0.5 times the tone. And in general, we need to take the magnitude of the 2. So again, we assume that the sine would be something like the imaginary part of this complex exponential. Right? This is where it originally came from. The sine part was the imaginary part, and the cosine part was the real part. And now we compute the magnitude. And again, we compute the magnitude by squaring the sine part plus squaring the cosine part, and then take the square root. So this is what you see here. Right. So this basically takes the magnitude, and in general you need both parts, but in our example the cosine part disappears. But this is just a special case. Yeah, so now we can try it. So maybe up to here, copy, paste. So now we can check it. Plot low pass down mix AM sine. This is how it looks like. So this is the sine part. So why does it look like a dirty sine or a smeared sine? Why is it such a thick line instead of just a thin line?
We zoom it.
Yeah, we can zoom it, right. Let's see what's in it. So, maybe look at this part. Can you see it? So it contains this high frequency signal. Where does this high frequency signal come from?
I assume it has to do with the low-pass filter not being as precise or not having as much attenuation as we wish, and therefore there's still some high-frequency spectrum left.
Exactly.
But not as much as before.
Yeah, exactly. So this is basically the rest of our carrier. Right? Remember, our filter is actually quite a bad filter. Right? And this is how it shows.
Or can we get a perfect low pass filter?
Well, you can never get a perfect low-pass filter, unfortunately, but you can get easily much better ones. So I have a particularly bad low-pass filter here. And this is what happens when you have a bad low-pass filter. Then you have the rest of your carrier frequency. And this is actually double the carrier frequency, because remember, in mixing we have the sum and the difference. So the difference now contains our original sine function, because we have carrier minus carrier, so the carrier goes to 0. And then we have carrier plus carrier. Right? That means we have twice the carrier function. And this is what we see here. So this is double the carrier function, carrier frequency. So we can also check the cosine version. Yeah, same thing, right? Basically it's 0, but we still have some carrier left. And this is what you see here. Right? When you see the values here became much lower, but it's still a significant part left. And that's because our filter is not so good. Yeah, and then we can take a look at this magnitude. So basically squaring on both parts. I guess now I can do plotting here. Oops. Oh. What happened? Copy. Paste. So this is now after taking the magnitude. And you can see it basically looks like the cosine part alone. Right? So again, this smeared sine function with an offset. So this offset from 0 comes from the amplitude modulation. Remember we had this 1 plus 0.5 times the tone, and this is what we see here. Right? The offset is the 1. Makes sense? So why is this 5000 and not the 1? Any idea? So basically this is this factor of A. Remember in amplitude modulation we always have this factor of A, which depends on the strength of our transmitter and the strength of the received signal. So we always have some unknown factor. And in this case, actually this unknown factor comes from using an unnormalized FFT. Right? So this factor actually depends on the length of our FFT that we apply. But that's the problem in general with amplitude modulation. In general, we will have a factor A which is not really known. Right? So we have to normalize it, and that's usually done using automatic gain control in the receiver. So the receiver always normalizes the signal to a certain desired output. Yeah, and this is actually one of the shortcomings of AM. You cannot really transmit absolute values. It's always relative. Because the absolute values are lost. Yeah, so we get this 1 plus s back with a scale factor. Right? And the scale factor is unavoidable. And the remaining carrier at double the frequency, because of our limited attenuation of our low-pass filter. So here, this is what I just mentioned. In this case, the cosine carrier would not really be necessary, since the sine carrier already has the exact same phase as in the transmitter. But during transmission, you get unknown transmission delays and thus unknown phase shifts, which makes the cosine carrier important. then you're independent of those shifts. Yeah, makes sense so far? So this is how you can transmit information over wireless channels. And this is actually still important to this day, even though it's a very old modulation form. But it actually gets a revival using so-called quadrature amplitude modulation in the digital age. And we'll come to quadrature amplitude modulation a little later. So first, a Python example for digital AM image transmission. So now we can also use amplitude modulation not just for an analog tone, but also for digital information. Right? So we would like to transmit our binary files from our image coder via sound and amplitude modulation. So remember, we already have this little image coder which can compress a color image down to, I don't know, 5 kilobytes, I guess. So a very small amount. So we have a small file with bits, which we now want to transmit. Right? And how do we transmit individual bits using amplitude modulation? Do you have an idea? How can we transmit bits instead of a tone? And first we need to distinguish the 1 from the 0. Right? And we need to give the 1 and the 0 different signal shapes so that the decoder can distinguish between a 0 and a 1. Right? And the simplest way would be to give the 1 a high value and the 0 a 0 value. Right? So if you have a tone, then this is the 1. If you have no tone, that's the 0. That's the simplest. It's usually not the best, but it's the simplest. Yeah, so for our little experiment, for testing, we take a short example bit sequence and write it into a test file because testing is easier with just using a few bits. And with Python interactive mode, which I just did, so I'm still in IPython, we import our Python file, which means we load all the function inside and don't execute them there yet, and then execute the desired function in the interactive shell. So here, this is what you already did. We have our write read bits library, and we can write this binary sequence to test.b. So paste. Yeah. So now we wrote this sequence here. So basically we wrote the sequence of 1, 0, 1, 0, and in the end we have 8 ones. So altogether we have 1 byte, 16 bits. Can you see that? So this is 1 byte. And we should also check if it's really there. So for that I open another window here. Ooh, this looks funny. It's better. Plus. So now we can check if we really created it by using the Linux terminal command xxd -b. xxd shows binary input or the binary content of a file, and -b means it displays at binary numbers. Right. So this is very practical. It's a little bit exotic command, but if you know it, it's quite practical. So I just go to my Linux terminal shell and execute this command. So here you can see it. Right. So you can see here, the first number here is the line number. So this is line number 0. It only has line number 0 because it's the only line. And this is the content. So we have 1 byte containing this 1 0 1 0, and then we have 8 ones. So this is exactly what we just output. So I can also check if it's just created. Hopefully, ls minus L for long. And we can see, yeah, it's today and it was 3 minutes ago. So we really just created this file and it has the desired input or content. Right. Yeah, so here I took advantage of the function that we created a few weeks ago. Yeah, so for our transmission we will read in the file again. So this file you have to imagine now as our image. Right? In general we have some binary image which contains the image. We have some binary file which contains our image. And here we just made it easier by just having 1 byte in this binary file. So in general we will first read from this file. So copy, paste. And here the bit string now contains our sequence. So this shows we are able to correctly read from this binary file, which in general will be our image. So then the bits from the file are modulated on 2 carriers using AM. So why 2 carriers? Because our information bits are modulated on the carrier with 1 kHz. 1 kHz to make it audible and also to allow transmission over usual speaker and microphones. Right? So in general, in wireless communications, this would be a much higher carrier frequency, for instance, several hundred megahertz. Right? So sound as transmission medium is kind of unusual, but has the advantage that our ears can pick it up. So for the modulation, the 0 bits get the value 0 and the 1 bits get a fixed high value. So simple enough. The length of the bits depends on the desired transmission speed or bit rate. The sequence of the bits is modulated directly on the carriers, which means multiplied, because we don't need to offset it. Right? They already are positive. The addition of the 1 for amplitude modulation is not necessary here as the bit signal is already positive. But now additionally we use a second carrier at 2 kHz which transmits a so-called clock signal. The clock signal changes from 1 to 0 if a new valid bit is present on the 1 kHz carrier. Otherwise we might have problems determining where a bit starts and ends. Right? So for instance we have a long 1 sequence, like the end of our example byte. We have 8 bits in a row. And that means the carrier is just constantly on. And if our receiver doesn't have the precise same clock as the encoder, then it might miss one of the bits or thinks there's one too many. So that's why we need to have the clock to synchronize the clocks of encoder and decoder. To tell the decoder where a new valid bit is present. Yeah, so the amplitude modulated signal of bits and clock is stored in the sound file, amfile.off. So this file is a sound file which we can then play back on the sound device, on our computer. For instance, using the play command or the aplay command in Linux. Then we will hear it on the speaker and we can pick it up with a different device with a microphone. So let's try it. So now we actually need to exit the IPython. And actually I can also do it here. Python am communications.py. So here you can see the signal that it creates. So remember, here we see two carriers, but we cannot distinguish them because they are both too high to be drawn. They are all just creating this blue color. And you can see here in the beginning, we just have a carrier. And then we can see here those changing amplitudes. They come from the 1 and 0 bits. And you can see here those short bursts are the clock. Right? And here you can see those bursts appear smaller at this point because there's a 0 bit. So here there's a 1 bit, and here there's another burst, but it appears smaller because there's a 0 bit. Right? Same here. So this is the original clock rate, and it continues here. It's just that we don't see it in this plot anymore. Right? Maybe when we zoom in, we can also see the different carriers. Let's try. Yeah, a little bit. So you can see it's not a pure sine, but it's a superposition of two sines. Right? Because if it would be just pure sine, we wouldn't see those small ripples here in between. So here's the 0, that means we only have this clock signal. Here we have a 1, here we have a clock, and the signal frequency. Make sense? Yeah. So here you can also see as while it creates the bits and the modulation. It prints then the 1, then the 0, which means transmit 1, transmit 0. So this is how it creates the bits and the clock signal. So now we can take a look at the created file, am file .dwarf. And you can see, yeah, it's now 2 minutes ago, right? We really created this am file.dwarf, and now we can also play it. Play am file.dwarf. Could you all hear it? So try to listen to the two different tones. Actually, your ear can pick up much easier that there are two different tones than you can see it on the plot. So there's a low tone and a high tone. So the high tone is beep, 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 right? And then there's this lower tone which sometimes goes off. So da, 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 da. Right? So the low tone contains the bit information. This high pitch beep, 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 beep is the bit rate, the clock for synchronization. Yeah, so this shows you that it's actually advantageous to listen to the sound, because here you can, using the ear, you can really distinguish those two tones. Yeah, so I'm using the play command here, which is part of the SOX library in Linux, which is often not installed by default. So if you don't have the play command, you have to type sudo apt install SOX. And it's part of this library. So SOX contains an entire library of useful audio functions. So it's actually quite practical. You can also use, instead of play, we can also use our Python program pyplay file. Right, it's doing the same thing. So let's try if it's still working. What happened? Oh, wrong window. Yeah, so this is basically doing the same thing, except now you can look inside pyplay file what it's doing. Yeah, and this sound can then be played back by the transmitting device, for instance a Raspberry Pi or smartphone, and recorded by the receiving device, for instance, on our laptop with our Python program, Pyrec audio file. So here, in this way. And let's see, maybe I can use my little iPhone if it has this example on it. So I'm usually using my little iPod Touch for playing back the sound. So you can imagine this takes a picture, then this picture is transmitted or converted into AM sound, and the sound is then played back, and in this way wirelessly transmitted to the laptop, right? Just using the speaker. So let's see, I have it in Dropbox. Let's try Nextcloud. Do you all know Nextcloud? This is a file server provided by TU Ilmenau. So all the students can get a Nextcloud account. And this is good for exchange of files. So I think everybody can get several gigabytes of storage. And it's for free. So everybody who has an account, who is a student here, can get a Nextcloud account. You just need to write an email or something and then you get it. In file. So this came from my little iPod Touch, and you can actually try recording it. Pyrec audio file. And this one here. So first I need to start this one, and then immediately after this one. Let's see. Recording a long time. I just set it to record a certain given number of seconds, and the rest is then just noise, which hopefully doesn't disturb the demodulation. So now we can listen to this recorded file using my command play file. So now you could hear room noises and echoes, right? So that shows that there's now disturbances on it. So now we can trying to read this received sound file and demodulate it, and it displays the decoded data and saves it in the file amdecoded.bin. So here, this is AM decoder bit string. Let's see what it's doing. Wow. So this is the AM signal that it recorded. You can see it really looks dirty, right? So you can see in the beginning, it's doing something, but then here, it looks like a gain control, which is, no, actually this should be the silence. So here in the beginning, this should be the actual signal with the bits. Yeah. So this should be the beep in the beginning, and here you can see the clock signal. And you can see it really looks dirty, right? It's much noise and distortions. And this also shows the beep in the beginning is important because the recording device usually has a gain control which adjusts the gain to the right level. And since AM is very sensitive to the gain, we want to wait until the gain control settled on a fixed value. Right? That's why this beep in the beginning was important. So here you can see indeed it more or less is settled on a constant value for the gain, and then those peaks are more or less at a constant height. So this is kind of a trick that we need to apply because the AM is sensitive to gain values. So here I can also zoom in a little bit more to the beginning. So here's the zoom. Yeah. So here you can see this should be the clock signal and the 1 signal, and then this should be the 0 signal in between, I guess. It's kind of hard to say because it's noisy, so we never really get down to 0, right? There's always something going on in the room, so it never goes to 0. And then also the full signal is kind of fluctuating. So that's why we need to have a decision value and a good value somewhere in between. And then the decoder says if it's above this decision level, then it should be a 1. If it's below this decision level, it's a 0. Right? And this coming up with this decision level is kind of crucial, because each time you make a wrong decision, you turn a 0 into 1 or vice versa. Right? Yeah, this is then the frequency response of our low-pass filter. You can see actually I used a slightly different low-pass filter which has much more attenuation now. So here we can see it has about 80 dB attenuation and below frequency 0.1. So it's much more narrow band. And I did that because it turns out using the other filter makes it too sensitive to room noises and distortions. Right? So the more narrow we make this filter, the more robust the transmission becomes. But it also means that the bit rate becomes lower, right? Because the passband of this filter becomes more narrow. So this also determines the speed of transmission. So when you want to make the transmission more robust, that means we need to make the filter more narrow, but that also reduces our transmission speed. And this is also the reason why when you have very weak signals, like from satellites from Mars, for instance, you only get a very low bit rate. Because from Mars you pick up a very weak signal and you need to stretch it over a long time to be able to apply very narrow band filters to get rid of all the noise in the transmission. Yeah, so this is the demodulated clock signal. It actually doesn't look too bad, right? So here, more or less, we correctly demodulated the clock signal from our 2 kHz carrier. So this is a prerequisite for correct demodulation. First, we need to demodulate the clock, because without the clock, we cannot decode the bits or demodulate the bits. Right? So this is an important step which needs to be done right. And here we have the demodulated bit signal. Yeah, this looks kind of funny. So here this comes from the tone in the beginning, but since there is no clock signal, it doesn't matter, right? right, the decoder will ignore this part. This part is the sequence of 1, 0, and you can see indeed it has 1s and 0, it goes up and down, as it should be supposed to do. And here is a sequence of 1s, and you can also see the sequence of 1s you can only demodulate because we have the clock signal to distinguish between the different 1s that are direct neighbors. So now we just have to make sure that we have the right threshold, the right decision level, to distinguish between 1 and 0. So when I zoom in here, so this is the interesting part. Oh, it's not good. So zoom into this interesting part here. We see that the threshold needs to be, I guess, at least above 500, right, to detect this part here as zeros. And it needs to be below 2000 to correctly identify the ones, I guess. Can you see that? So actually in this case we have quite a nice distance between zeros and 1. So to find the right threshold should be not too difficult. It's getting difficult if they're getting too narrow. Right? If the distance between zeros and ones is becoming too narrow, then we more easily get errors. So, right. So now this is the bits and clock after threshold operation. So the blue is the clock signal, and the red is the bit signal. So again, here nicely it ignored the noise that came in the end of the recording, so correctly. And here in the beginning it detected this tone that we transmitted for the gain control. But since there was no clock, it doesn't matter. So here you can see the blue is our clock signal, and the clock signal alone turns the signal into bits. So here we can see that we have nice levels after thresholding. So when I zoom in, yeah, you can see it. So here you can see each time the clock goes down, we detect a bit. So that works nicely, it seems. So the clock goes down here, then it goes down here where we have a 0, then it goes down here where we have another 1, then it goes down here where we have a 0, and it seems the thresholding did the right job. So my guess is we do the right decoding here at the next step. Does it make sense? So you can see the decoding for the binary part consists of a few more steps. Right? So we need to have the thresholding. This is this additional step, which we don't need for the tone, for the analog transmission. And then we need to have the decision where we decode it. Right? And that's why we need to have this clock signal. So we see the separation of clock and bit signal is not perfect due to our imperfect filters, but sufficient for our purposes. Even after an acoustic transmission, most of the bits can still be decoded, although we can observe that the waveform has changed considerably. So let's see what it decoded. S minus LT more. So this command is actually a trick when I want to see which were just the recent files that were generated. I'm just using the option minus LT, where the L means long and the T means the most recent first, right? Ordered by time. And more means it just lists one screen after the other. So here we can see it. AM decoded. So this came just out. And now we can take a look at it with this XXD. So saying copy. So xxd minus b, AM decoded. And now you can see what's inside. Wow, we actually have a totally perfect decoding. Right? It's exactly the same, no bit error. I'm surprised. That's really good. Often we have some bit errors. Yeah. So here you see the bits survive the acoustic transmission. So that's nice. Yeah, maybe I should add that here. Take a look at the decoded bits in the Linux terminal shell. Should write this capital. If we are lucky, this is the exact same as for the modulator. Yeah, and since basically we can use any arbitrary file, we can also take a small text file. Right? The text file basically is a special kind of binary file. Right? It consists of ASCII text. So here, for instance, this test.txt. So here I can take a look. More test.txt, it's already there. Yeah. Can you see it? So more shows you the content as ASCII, and here it shows you TU Ilmenau. Right? It's just this short text. And now we can just use this text as input. Or here you can look at it in the binary form. Copy and then see the sequence of ones and zeros. So here you can see it takes a few more bytes. Right? So in here you have the first 5, I guess. 1, 2, 3, 4, 5, 6. And here you have 1, 2, 3, 4, 5. So you have a few more bytes in this case. And you can see the ASCII code of those letters. Right? So the first byte, this 1, 0, 1, 0, 1, 0, 1, 0, 0, is the ASCII code for T, capital T. Right? So each letter consists of a code of length of 1 byte. Are you familiar with that? So basically this is how ASCII code looks like. And then you can just transmit this file. Yeah, we just modify this code to read on and to read in this file instead. So copy, gedit. Oh, didn't work. am.com.py bitstream. So here you can now see the code. Yeah, here's the 1-bit defined with modulation, here's the 0-bit defined with modulation, and here is the bit string. Oh yeah. It already has this test.bin, and now we want to have test.txt. this out. So now we have a different input, and we can let it run again. Python am com.py, and you can see here this is a correspondingly longer sound file, because now we have 11 bytes, and I can also play it. What was the output again? Star.morph. File, this one here. ls minus long. Yeah, it's today. And now I can say play. Almost sounds like Morse code, right? It's coming from the sequence of zeros and ones. Yeah, and then we can also play it back. Let's see if I have it on my little iPod already. It should be there now. Right. Quite. But I have an already recorded file, which sounds like this. Play. You can hear it's much softer. And this again comes from a recording using sound as transmission. And then basically we can do the decoding in this way. And here's the decoding. So I skipped the recording here because of time issues. So I just want to run the decoder on this file. And here you can see the resulting audio file. Again, you can see it looks really dirty. So here's the same filter. Here's the demodulated clock signal, which looks okay, more or less. Here the demodulated bit signal. And here is then the signal consisting of the clock and the thresholded binary values for the information bits. So you can see it's basically much longer than before. And here's the decoded bit string. And let's see what it wrote. ls minus l t more. So AM decoded. Yeah, and here we can see it probably best using first xxd minus b. So here you can see the bits, and you can also already see that the correct bits are received because we got TO Ilmenau. And you should also see it by using the command more. Yes. So here you can see, indeed, it decoded TO Ilmenau. So now we have a wireless text transmission. So this we could use, for instance, to transmit SMS via sound. right, using AM. So this could be something practical actually for transmitting secret messages using sound or something. You could also think about it using ultrasound, then it's unnoticeable, right, because you cannot hear ultrasound. Yeah, questions at this point? Make sense so far? So maybe after the lecture you can take a look at the code and see how I implement it and maybe try it out yourself, maybe using some text and then transmit this text via sound. Okay, so thanks for your attention and have a nice rest of the day.